موعدنا مع كل من أرماندو أليوت وكريستوفر هام من معهد ستيفز للتقنية، ويمثلان الفريق الفائز بالمسابقة العالمية لعام 2015.
Thank you, Mr. Nelly, for this very informative presentation. And now I would like to welcome Armando Elliott and Christopher Hammm from Stevens Institute of Technology, Solar Decathlon Winning Team 2015.
Thank you so much to DEWA and Solar Decathlon for inviting us here to Dubai to present. My name is AJ Armando, and I'm joined by my colleague Chris. We just have a short video to play first, and then we'll get into our presentation. If you could cue up the video, please.
In October of 2012, Hurricane Sandy wreaked havoc along the northeast coast of the United States. In New Jersey alone, there was an estimated $29.4 billion in damages, with 346,000 homes affected, and almost 2.5 million people left without power. The destruction the Stevens community experienced here in Hoboken challenged us to respond positively in the face of this disaster.
Welcome to the Shore House, Stevens Institute of Technology's entry into the U.S. Department of Energy's 2015 Solar Decathlon competition. The Shore House started with a simple question: can we design a home for coastal regions that dramatically reduces energy use while also protecting us against the realities of an ever-changing, increasingly extreme climate? A truly sustainable home should also be resilient, an idea that has driven the design of the Shore House. This 1,000 square foot home is well tailored for the Jersey Shore, taking many of its design cues from the area's rich history and culture.
Behind the durable cedar-clad exterior is an open, two-bedroom, one-bathroom home. Informed by life at the shore, the home's living space opens to the outdoors.
The interior has a bright, contemporary coastal aesthetic, creating a welcoming space for cooking, dining, and living. A gracious kitchen island with induction cooktop and induction chargers creates a flexible central gathering space for residents. The bathroom allows entry directly from the deck, convenient when returning from the beach.
Built to the rigorous international standard of the Passive House Institute, the Shore House is blanketed with twice as much insulation as a conventional home, while being 10 times more airtight. The heat recovery ventilator recycles heat from outgoing stale air and uses it to help condition filtered fresh air all year round.
Our well-insulated triple-paned windows enable the Shore House to use 90% less energy for heating and cooling.
To protect our home from an oncoming storm, our team has drawn inspiration from the marine industry. The floor and walls are clad in a thick, durable plastic sheeting and sealed with marine adhesives. Our fiber composite storm shutters and plugs enable the residents to seal the home in preparation for a storm. Student designed and fabricated, these unique shutters provide optimal shading during the summer and direct solar heat during the winter. The shutters also feature building-integrated photovoltaic panels which supply efficient hot water to the home, even through a power outage.
The main rooftop solar array provides ample power for mechanical equipment, appliances, and an electric vehicle. The array is able to island or isolate itself from the power grid during a blackout and provide safe, clean, renewable standby power while the sun is shining to help serve the community during post-storm power outages. We're building innovative solutions for a world increasingly affected by a changing climate and doing our part to help the New Jersey Shore bounce back from the damaging effects of Hurricane Sandy. Shore House, a new direction for coastal housing.
Great. So, as I mentioned, my name is AJ. I was the student electrical engineer and communications lead for this project at Stevens, and Chris was the environmental engineer. Respectively, our backgrounds are in those areas, and then we're both as part of a graduate program, architecture students, where we work with other architecture students and engineers. So we participated just this past fall in October of 2015 in Irvine, California in the Solar Decathlon competition. As previous speakers had mentioned, it was a 10-day contest and had 10 categories. So some of the more new ones included commuting, where we had to charge an electric vehicle off of our home, energy balance, where we had to produce more than we consume, but it also introduced the aspect to the competition where we had to consume less than a certain amount over the course. So we had to first and foremost focus on energy reduction and then focus on introducing renewable energy resources. So this was not our school's first time competing in the Solar Decathlon. We competed once before in 2011, or twice before in 2011 and 2013. In 2011, we partnered with another university in New York City, as well as an institution called Habitat for Humanity, which works to get low-income housing to the less fortunate in the United States. And this home, which got 13th place in the competition, was a very great learning experience for our schools and for the students working on them. And then this home actually got first place in affordability that year, which was really the goal. Going forward to 2013, we got 4th place, and this home was it's called the Eco Habit Home. Introduced a lot of interesting concepts. It had building integrated photovoltaic panels, got 2nd place in architecture, which was a really major accomplishment, especially since our school doesn't actually have a college of architecture associated with it. But about halfway through this project in 2012, we got hit by Hurricane Sandy, as the video just showed, and as many of you may know. And that really, really impacted us on the northeast coast of the United States, but also more significantly in New Jersey, particularly where our school is located. So just some of the statistics about this event. There was close to $30 billion in damages, over 2.5 million homes without power, and over 340,000 homes damaged. So it was a major, major catastrophe, and we wanted to respond positively in the face of this disaster. So that's where we came up with the notion of the Sure House. So the Solar Decathlon does an excellent job of encouraging schools to make sustainable solutions for their respective regions. And we found for our region that one of the main aspects of sustainability was also resiliency. So building a home that can help mitigate climate change, but also survive and brace for the effects that are becoming more real with increased storm activity and weather events. So the Sure House is a play on words, sure meaning certain, but also sure standing for sustainable plus resilient, and also a play on word for a shore home, which is a home located along the coast. So on the sustainability side, we first and foremost focus on radically reducing our energy consumption. Chris will talk more about our passive house techniques. And then we also implemented renewable energy to produce about 130% of our energy needs. And then on the resiliency side, we adopted a lot of practices from the marine industry to help best protect and shield this home in the event of the next 100-year storm, which we're finding happens a lot more frequently than every 100 years. So the scope of this project, we had about 60 students involved, 6 graduate students, both of which we are, about 10 faculty members. We're a relatively small university, so we got almost all of the departments at the university involved, and it was over the course of 2 years. So just some of the team breakdown here. So we're part of a program called the Product Architecture and Engineering Program, which brings together, it's a graduate program that brings together architects and engineers to collaborate. And we worked full-time for about 1.5 years on this project. And then we served as the main hub, which all the other departments went through. So mechanical engineering team, which worked on our heating and cooling systems, as well as our storm shutter systems to help protect the home from flooding. Civil and structural engineering teams to deal with a lot of the code-related issues for designing a home to withstand the hurricane-type conditions that we were designing for. Engineering management team to deal with a lot of the finances and project planning. Electrical engineering team to deal with the energy systems and also work closely with the computer science team to develop a home monitoring system. And what we found to be very important was sponsorship and community outreach. So we had a community outreach team that went along to different communities along the coast and do investigative reporting to determine what their needs are and really do market research to determine what the needs are of all these communities. So this is a image of the home. So the Sure House is designed, it's about 90 square meters interior with another 90 square meters of exterior decking space. So we designed with a very open floor plan. You can see in the middle here our living and kitchen area, which dominates the footprint of the home. We did design it as a 2-bedroom home because we really intended this to be having a family living in it. And then one of the more unique design features was our bathroom allowed entry from the exterior. So if you're returning from the beach and wanted to wash off, you can just go right into the shower without having the need to track any dirt into the home. So this is the entryway of the home. This is actually photos taken out at the competition in Irvine. This is our south porch here. We designed these privacy shades since a lot of these communities are very, very close together as far as the lots are. So to have outdoor space where you can be connected to the outdoors but not be connected to your neighbors necessarily, so you can still have an element of privacy associated. This is, again, the south facade. The interior, you'll notice we chose very light colored materials. This is a birch and white paneling, and that was done as a design decision to maximize the daylighting in this space so that we virtually never have to run electric lighting while the sun is out. And here is the home as it's coming apart in New Jersey before we sent it out to California. So as many of these presentations have shown before, many homes are designed modularly, so in the very short time span that you have to put them back together before a competition begins, you really want to minimize how much you actually have to do at that phase when you have all this construction time leading up to there. So we designed our house to be 3 modules and then all of our decking to be flat pack panels. And we ultimately took it apart. These 3 modules made it onto tractor trailers, and then all the extra materials made it onto a 4th tractor trailer. And we had to ship it 4,000 plus kilometers to the other coast, and currently it's waiting to come back to the East Coast as we speak. So this is a shot, photo taken right after Hurricane Sandy. This is actually on my cousin's porch. So these are very real effects that many of us realized. We're also noticing there's a major trend for even more people to move closer to the coast. So in the United States, there's supposed to be an 8% increase of population living in counties located directly on the shoreline. So it's not like more people are moving away, more people are moving to the coast. And as rising sea levels become more of a reality, as well as increased storm activity, a lot of these issues of resiliency become more and more important. So FEMA, which is a government agency that handles a lot of these natural disasters, as well as the National Flood Insurance Program in the United States, responded after Hurricane Sandy with restructuring the way that they determine the floodplains and also making building requirements for homes to be raised above these floodplains. So this is an example of a home that was once low to the ground, but then had to be put up on these pylons in order to be code compliant in the event of a storm coming through so that water could pass underneath. We found this to be an opportunity to design a prototype that could remain low to the ground, remain engaged with the community, but also aesthetically pleasing and accessible for those that might be in wheelchairs or things like that. So while FEMA wanted homes to respond like this, we designed the Sure House to still be low to the ground, and it was intended for a specific flood zone called an AE flood zone, which probably don't have to deal with that much over here, but it's basically rising tides, but not wave action. So the loads associated with wave action would be much too intense for us to try to engineer. So our floodproofing methods, so this was one of the major innovations on the project. As I mentioned before, we adopted a lot from the marine industry. the boat building industry, and we actually had a few members of our team that had experience building boats and yachts, and also in architecture and applying those technologies to architecture. So for our wall assembly, you'll see we had a layer of plastic adhered to the walls and underside of our home, where all the seams and penetrations were caulked and taped to make a continuous flood-proof shell. And that was a great solution for the walls, but windows created another design challenge. So we designed with what's called fiber composite materials that are becoming more and more popular in architectural applications, mainly because they produce a very, very strong and rigid building material, but also are relatively light and can be engineered for the specific applications and specific loads that you have to use them for. So we designed these flood-proof composite shutters that you see when they're in their up position, they serve as a passive shading device, designed optimally to allow the winter sun in to help heat the home, but block the summer sun from coming in to minimize how much we need to cool the home. And you'll also notice that they have solar panels on them that help to heat our hot water. I'll talk about that in a minute. But when they're deployed, when they come down, they fully enclose the house and latch in and provide continued protection. And for the other windows and doors, we have similar panels that are able to be screwed in and continue that protection from around the home. So more about our energy systems. So we actually had two different types of solar arrays on the Sure House. One shown in yellow here was on our roof. It was a 9 kilowatt array. And then the second one on those storm shutters was about a 1.8 kilowatt array. The roof array, much like many homes have, was tied into a central inverter system and provided more than enough energy for the home, like I said, about 130%. And then that shutter array was direct DC energy that went into the lower heating element of our hot water tank. So the main array had the ability to do what's called island or isolate itself from the grid. So many people in New Jersey and in the United States in general, they install solar panels to try to be more green, try to be more sustainable, and they also think, well, in the event of a blackout, I won't be without power because I'll have solar panels to help power my home. What they don't realize is if they're tied into the grid and they don't have a battery backup system, they go without power just like the rest of their neighbors, and then they're wondering about this investment they just made to install solar panels. So this inverter that we use for this home actually has the ability to island, so it can detect when the grid is down. And in the United States, we deal with an aging infrastructure, particularly an aging electric infrastructure, where a lot of the power lines and distribution system is very subject to going down in the event of weather storms. I know the blizzard that we thankfully dodged by being out here in Dubai this past weekend affected hundreds of thousands of people with power outages. So it's a very real issue. Excuse me. And so when it detects that the power grid is down, it's able to switch over into what we call Resiliency Mode and still provide a certain amount of backup power to the home that we actually, for the effort of a design competition, we routed this power to charging stations on the house. So we had outdoor USB charging stations and indoor induction charging stations, as well as a convenience outlet that allows community members to come by and charge their devices off of our clean solar energy rather than firing up a diesel generator, let's say, and trying to power their devices off of that. And it also allowed them to remain in communication in the event of a disaster like that. Our hot water system. So many people might be familiar with solar thermal systems, which are much more common as a renewable way to heat hot water. In the Northeast, though, with major temperature differences from the summer to the winter, we found this to be a good prototype for a different type of way to heat our hot water. So when you design a solar thermal system to maximize, to have production in the winter time, you oftentimes have way too much hot water being produced in the summertime, and the system can go over temp and over pressure. And when you design it to have optimal production in the summertime, you end up having to deal with way underproducing enough hot water in the winter. So by having the electric array, which wires as direct DC energy as the heating elements to heat hot water, we were able to optimize for the winter, and in the event of overproduction in the summer, the solar panels are just able to go to open circuit and shut off, which was really beneficial. And then that was also paired with a hot water tank that had a heat pump available on it, so that it was able to recycle hot air in our mechanical room space and use a compressor to recycle it into the hot water, so that we could take the equipment, like our inverters, for instance, that throw off a lot of hot air, and recycle that. And finally, for the energy systems, we installed a pretty comprehensive home monitoring system. So the home monitoring was threefold. We had environmental monitoring, which included temperature, humidity, and indoor air quality. Our house was very, very airtight, which Chris will talk about, which introduces an issue of indoor air quality, CO2 buildup, especially if there's any issues like mold. We monitored our hot water system. Since this was a very new, innovative system, we wanted to know exactly how it was running and operating, so flow monitors, things like that. And then, kind of most importantly for the Solar Decathlon, was our energy balance. So we were monitoring on a very, very resolute level all of our energy consumption and all of our energy production. So this gave us the ability as an academic project to verify a lot of our assumptions and a lot of our modeling. So this is a few days over the summertime, this past 2015 summer, where in blue you can see what we modeled based off of the projected weather data, and in yellow you can see what we actually got. And it really helped a lot of our students and modeling teams to verify their models. And then when I say highly resolute, as far as energy monitoring, we were able to really, really track closely exactly where all of our energy was going, which we found to be very important. So this is kind of a bit comical as an example, but for these meals that Joe and Richard mentioned, we were able to know exactly how much energy was going into making each course of the meal. We were able to know exactly how much energy was being used to cool the home during the times of these cooking events. And that allowed us to do several dry runs of the home and really learn about the best and most optimal way to operate the home. So with that, I'll turn it over to Chris, who's going to talk more about our energy efficiency.
Thank you, AJ. So, as AJ mentioned before, we are the Sure House. We are both sustainable and resilient. And one thing that we believe is that a home needs to be sustainable, needs to, first and foremost, focus on reducing energy consumption, much like Kiara mentioned before we even talk about producing energy. And so to do that, we adhere to what's called the Passive House Building Energy Certification Standard, which comes out of Germany. And there are 6 main sort of tenets that you have to follow to adhere to the Passive House Building Energy Standard that sort of drove our design, which I'll quickly lay out for you. First, you need to use the sun during the winter. Heating is a very, very large part of our energy consumption, especially where we're from. You need to use the sun, but optimize for it. So in contrast, you need to control the sun during the summer to keep it out to also reduce your cooling demands. In addition to this, our house had a very, very efficient envelope. So the first tenet of an efficient envelope for a passive house, very high levels of insulation. We had about twice the insulation required by code. We were incredibly airtight. Our house was about 10 times as airtight as a typical home back in New Jersey. We designed our details to reduce what's called thermal bridging, which is a very high level of energy loss throughout the winter, especially in our area. And finally, we used something called an energy recovery ventilation system, a way in which in a very airtight house like ours, you're able to actually recover the heat that you put into the air as it passes by through a heat exchanger through your ventilation system. So with all of this combined in a very sophisticated energy model, we're able to show that our house is projected to use 91% less energy than the average New Jersey home. Granted, the average New Jersey home does use a lot of energy, but this was all by employing these passive house measures. So I mentioned our energy model. One very important part of our project was trying to use all the climate data available to us and all the most sophisticated models we could to try and project how much energy we're actually going to use throughout the year. So one of the most important ones to use is called the Passive House Planning Package. It's something that is required for certification for a passive house. And so this just sort of gives a breakdown. The whole point of having such an efficient envelope is that it gives you the ability to have the control to balance your gains and losses inside the house, the heat gains and losses, to reduce your energy needed for heating and for cooling. So this just gives you a little breakdown of the output of our energy model. On the left, it shows the heat losses. This is in particular in the winter, in the heating season. Shows the heat losses. You can see that we have losses through our ventilation, through our windows, through our roof. And then on the right shows our heat gains. You can see a lot of our gains come from our windows, from our south windows in particular, gaining heat from the sun. What you can see at the top is what's needed to complete that balance, and that's the final sort of heating demand for that season. Through this calculation, we were able to show that we would pass the passive house certification. So to try and, again, help the research in the energy modeling world, which is an ever-growing area of research today, we also wanted to use other types of energy models, some more sophisticated energy models, especially an hourly energy model. One that we use is called Transys, and I believe Kiara's team might have used it on their project as well. This is a way to see how much energy you're going to use on an hourly basis throughout the entire year. This graph, which is a little hard to read, I'm sorry, shows our heating and cooling demand along with the indoor and exterior temperatures. And basically what this gave us the ability to do is see where throughout the year we're going to be using the most energy, where are going to be the big problem areas for us. This then gave us the ability to compare with other types of energy models. The PHPP is a monthly model. This is an hourly model. And so this is, again, just to try and help, since our house is very highly monitored, as AJ said, to try and help provide data and research for the energy modeling world. Here you can see sort of a tally of the gains and losses of these calculated by these two different models. You can see a high level of correlation, but not exact. It's a very hard thing to do to model a house, and that's something that we're trying to deal with and trying to further the research on. So here's just a quick look at our typical details. Look very similar actually to the house from Italy, but you can see what we had to do here is we really had to use interesting measures to reduce our heat losses and increase our insulation. So you can see in our walls we have a triple layer of insulation, a layer on the outside, basically acting as a blanket covering the entire house, 5.5 inches on the inside of the wall cavity, and then another 2.5 inches on the inside of the wall, creating an incredibly thick R40 wall, which is about twice the code that's required back in New Jersey. To try and assess these details and assess all the connection points in our house, we used an energy model that's created by the US government called THERM that actually calculates the heat losses through what's called thermal bridges in your connections. So when you have a point in your wall or your floor where you have a high amount of conductive material compared to the insulation around it, that can cause basically a heat sink and can be can cause heat losses, but can also be a problem for condensation and mold. So we have to evaluate every single connection detail to make sure that this is not going to happen. This is just an output of what that looks like. And you can sort of see here the lighter colors sort of show where the heat is flowing through our envelope. And we were able to design to try and basically decrease these as much as possible. You can also see in this graphic the red dashed line that shows our air barrier, our continuous airtight layer that goes throughout the entire house, which allows us to be 10 times more airtight than a typical home. In our window details, we have our triple pane windows, again with this continuous airtight layer and a very highly reduced level of heat flow. in our ceiling to wall connections, again, you can see this exterior layer completely wrapping up the side of the house and cutting off that heat flow between the walls and the ceiling, which can often be a very big problem in houses in the U.S. So I mentioned air tightness as being a very important factor in reducing energy consumption, and I keep saying that our house is 10 times more airtight. The way we actually test this is by pressurizing and depressurizing the house and coming up with a metric, a measure of how many air changes per hour will occur in your house at pressure. So compared to what's required by code, you can see this is actually a graph of the heating demand based on air tightness. Up at the very top is what's required by code, and us down there is what we were able to achieve right underneath the Passive House US standard. So here are just a couple photos from construction. The construction phase was incredibly fun. We could not have learned more. Definitely taxing at times. But here you can sort of see us. The students were involved in all of the insulating and air sealing measures in the house. Here we are insulating the inside of the walls, the outside, the exterior blanket, and then the interior 2.5 inches in our service cavity. Here we are doing the air sealing and the blower door testing that I mentioned. So you can see this sort of white fabric acts as it's a product that comes from Germany. It's a vapor barrier that goes on the inside of our walls and allows us to be so airtight. In that wall there, that red fabric is there we go. The red fabric, that's our blower door. So we seal that up in the door, we turn on a fan, it pressurizes the house, and it actually measures what the airflow is going to be through all the cracks in our walls and windows. This is us installing our highly efficient triple-paned glass windows that came from Germany. These are about 600 pounds a piece. I'm not going to be able to do that conversion for you, but incredibly heavy, so it took about 10 students on every single pane of window to get these in there. We actually had to take them out and put them back in when we traveled to California. And that's how they looked actually intact. Again, these were maximizing solar gains in the winter, and the solar shades from our storm shutters keeping out that sun in the summer. This is an overall energy balance that we were able to calculate, showing that we plan to be net positive throughout the year and actually be highly net positive. The hope is that all this extra energy could go towards our electric vehicle. You can see this is actually this is actually our consumption throughout the competition. We way overproduced during the competition. There was a lot of sun out in California, giving us a net positive energy production, even though we did go slightly over the energy cap that they put in this past year. So overall, we were very successful. We could not have imagined how great this competition would have gone for us. We ended up getting first place in all of the juried competitions, as well as a few of the measured ones, getting us first place overall. So with that, here's just the rendering of the Sure House down on the shore. Right now, we're taking the Sure House back to Stevens. It's going to go right on our campus, right across the water from New York City, and it's going to live on as Shore Labs. We're going to continue research with the energy modeling, the energy monitoring, and continuing the technology for flood proofing. So with that, thank you very much.